Swayam Prabha. Digital India. Educated India.
Today we will continue our discussions on internal forces. In the previous two lectures we saw how to determine internal forces in the structural members, and particularly we discussed about finding these internal forces in beams. The other class of structures that are predominantly used are cables. We will see how to analyze the internal forces in cables in this lecture. The cables, being flexible elements, are subjected to tensile forces only, because they cannot resist any compressive force and they cannot also take any bending moment. Some examples of cables are the suspension bridges, transmission lines, aerial tramways, guy wires for high towers, etc. So, in this picture you see a bridge that is being supported by these cables. So, this is the suspension bridge. You have these vertical cables tied to the platform of the bridge and supported by these cables. So, the primary concern in the design of such structures is to know the shape of the cable when the cable is loaded with various kinds of loads, could be concentrated or could be a distributed load, because accordingly we would like to know the lengths of the cable to be used so as to maintain, let us say, the platform in the horizontal position or in the required position. So, we will start the discussion with concentrated loads and then move on to distributed loading on cables. Here you see an example of a cable that supports concentrated loads. The cable is supported at A and at B and carries some concentrated loads, say P1, P2, P3, etc. at various locations C1, C2, C3. These loads are known as well as their horizontal spans are known. The interest is to know these y coordinates, that is the shape the cable will take once these loads are being applied to this cable. Certain things we can note, that for analysis we assume that these locations are given, that means the horizontal spans x1, x2 and x3 where these loads are applied to the cable are known. Also we assume for the current analysis the weight of the cable to be negligible when compared to the concentrated load. Else the shape of the cable will be different if we also consider the weight of the cable, because it becomes a uniformly loaded cable in that case. But for the current analysis we assume the weight is negligible compared to the concentrated loads. And also this resistance to bending is very low for the cables. So, these end reactions will be only force reactions and not any bonding moment. Between two portions, say C3, C2 or C3B, the cable can be assumed to be a two force member. This is because the loads are applied at C3 and at B and we are neglecting the weight of this portion. So, it becomes a two force member. And since we have seen that the cables can only be loaded in tension, the forces developed in this portion are tensile and their direction is that of the pulling nature. So, our interest is to determine these vertical coordinates of the point of loading, or in other sense the shape of the cable. So, let us consider the free body diagram of the complete cable in order to determine the end reactions. So, in this picture you see the free body diagram of the cable. So, you have at A two components of reaction AX and AY, because we saw that the cable cannot take any bending moment, and since the cable is fixed to this point A, the end reactions has to be only two force components and no bending moment. Same way at B the cable is fixed, so there will be two components of reaction BY and BX. Now, the shape of the cable is unknown, that means it could be something like this, the dotted line shown, or it could be something like this or any other position. And so, we do not know the end tangent of this cable, that is the direction of this line AC1, and also we do not know the direction of these lines, that is C3B. So, we have two unknown components at B and two unknown components at A. So, we see that we have a total of 4 unknowns are involved in this, that is AX, AY, BX and BY. If we consider the equilibrium of this portion for the two-dimensional cable layout, we can write 3 equations. From the force summation equation we get 2 scalar components, that is sigma fx equal to 0 and sigma fy equal to 0, and for the moments to be 0 we have one scalar component, that is the moment about the z axis, that is perpendicular to the plane of the problem. So, with these 3 equations we can only find 3 unknowns. So, since this problem has 4 unknowns, we need one more equation to solve this. So, it could be as a known point on the cable. So, if we know the y coordinate of, let us say, a point D on this cable, then it is possible to write additional equations to solve for the unknown. Let us assume that we know the coordinate of this point D on the cable. It could be any point, either in this segment or in this segment. If we know this, let us draw the free body diagram of one portion of the cable, that is either AC1D or DC2C3B. Let us consider this portion AC1D and draw the corresponding free body diagram. So, at D we have the tension of the cable, which is both unknown in magnitude as well as direction, that is depicted by this arrow, and we have these two unknown forces Ax and Ay, the reactions at A, and this load whose horizontal location is known and not the vertical location. We know this coordinate D both x and y, and so now it is possible to write an additional equation, say the moment summation equation about point D, and now we will have three equations from the earlier free body diagram and one more equation from this free body diagram, totaling to 4 to determine the 4 unknowns. So, this is the additional equation that we have, and now we have 4 equations to determine the 4 unknowns. Now, the 2 more equations, that is the force summation, will give the horizontal and the vertical component of this tensile force T, that is Tx and Ty. Now that we have determined these end reactions, it is possible to determine the tension in each of the segments and also the location, the vertical coordinate of the location of the concentrated loads by considering the free body diagrams of sections of the cable. Let us consider this section AC1 C2 and draw the free body diagram. Since we have determined both Ax and Ay, we know the tension that will be occurring in this segment, that is AC1. So, we do not need to consider the free body diagram of, say, the portion AC1 again, but now we do not know the tension in this segment, that is C1 C2, and so we take this segment and consider the free body diagram. The tensile force T is both unknown in magnitude and direction. So, we mark the same as both Tx and Ty as unknown, and we also do not know this y coordinate, that is the location of the point of concentrated load in the vertical direction. So, we can now write the equations for equilibrium. We take the moment summation about this point C2, and since this unknown force T passes through this point, we only have moments because of the concentrated load P1 and the moments due to this Ax and Ay, the end reactions. So, this equation sigma m C2 equal to 0 is Ay times the moment arm, which is x2, and this leads to a clockwise moment about this point, so it is negative, and AX has a moment arm of y2 again, which is clockwise, so it is negative, and this force P1 has a counterclockwise moment, so it is positive. P1 times the moment arm is x2 minus x1 equal to 0. So, in this we know Ay, Ax, this location x2 as well as P1. So, we only have this y2 as unknown, and that can be determined. The other two equations, that is sigma fx equal to 0 and sigma fy equal to 0, yields the other two unknowns, that is Tx and Ty. So, if we write this equation, let us say sigma fx equal to 0, it is Ax plus Tx. We have only these two forces equal to 0, and for this equation, that is sigma fy equal to 0, we have Ay minus P1 minus P2 minus T sin theta equal to 0. This is nothing but Ty, the vertical component. So, from these two equations, since only we have this Tx and Ty as unknown, the same can be determined. It is interesting to note that the horizontal component of the tension, that is Tx, which is T cos theta, is equal to this reaction Ax for all the segments. So, even if we consider the free body diagram of the cable for the portion AC1 or for a portion in between C1 and C2, at any point the horizontal component of the tension is equal to Ax. That is because we do not have any horizontal loading in the cable. So, the horizontal component of the tension is always equal to the horizontal component of the end reaction. This is useful in certain analysis. Let us see an example to illustrate the complete procedure. Here you see a platform which weighs 2000 newtons, is held in a horizontal position using cables. The cables are tied at this point E and at point A, and in order to maintain this platform in the horizontal position, we have the concentrated load P2, which is 500 newtons acting at a point B. This is to make sure that the cable takes a shape such that the platform is maintained in the horizontal position. The lengths of these cables AB, BC and DE and their inclinations are to be found. We know these horizontal spans, that is the span between AB, between BC, CD and DE. For this analysis, we assume the mass of the cable to be negligible. So, in order to proceed, we consider the free body diagram of the complete cable. The unknowns for this problem are the end reactions, that is Ax, Ay and Ex and Ey, as well as the forces at this point C, that is Cx and Cy. Because if we know these forces, that is Ex and Ey, then dy and dx are also known. So, the unknowns for this problem are 6, that is the horizontal and vertical components of forces at A, C and at E, or it could be otherwise stated in terms of the magnitude and the direction of the tension that occurs between various segments of the cable. So, here we have 3 segments AB, BC and DE. So, the unknowns can be restated as the magnitude and angle of these tensions in these segments, that is say T1 theta 1 for this segment AB, T2 theta 2 for the segment BC and T3 theta 3 for the segment DE. Now, let us draw the free body diagram of the complete cable. So, this figure shows the free body diagram of the complete cable. So, at E we have this reaction, end reaction, which is equal and opposite to the tension that occurs in this portion DE, that is T3. So, that is what the end reaction has been marked as T3 in the opposite direction. Same way at A, the reaction is equal and opposite to the tension that occurs at in the segment AB. So, that is why we have marked this T1 in this direction. And let us replace this platform CD by a concentrated load of 2000 Newton acting through its CG. Now, from the free body diagram, for the equilibrium of the cable to exist, the sum of the forces has to be 0 and sum of the moments has to be 0, and let us write the corresponding equations. Let us write the force summation along the horizontal direction and equate it to 0. So, we have the horizontal component of this force T1 acting in the negative direction. So, we have minus T1 cos theta 1. Then we have the horizontal component of this force T3 in the positive direction. So, plus T3 cos theta 3. We do not have any horizontal forces, any other horizontal forces. So, this has to be 0. So, let us say this is our equation 1. Now, for the forces to be 0, the vertical component has to be also 0. So, we have the vertical component of this force at A, which is T1 sin theta 1 in the positive direction. We have this concentrated load P2. So, minus P2 which is known, and the concentrated load, the equivalent concentrated load of the platform CD. So, minus, let us say W, which is the weight of the platform, which in this case is 2000 newtons. And then we have the vertical component of this tension plus T3 sin theta 3. Let us say this is equation 2. Then the moments have to be 0. So, let us take the moment summation either about E or A, where we have the unknown forces. Let us take the point E and equate it to 0. So, we have the moment of this force T1, the horizontal and vertical components of this force have moments about E. So, let us consider the horizontal component first, which is T1 cos theta 1. The moment arm for the same is 15 meters and it causes a counterclockwise moment about this point E. So, it is a positive moment. Let us consider the vertical component, that is T1 sin theta 1. It causes a clockwise moment about point E. So, it is a negative quantity. T1 sin theta 1. The moment arm for the same is this complete span, which in this case is equal to 80 meters. Then we have the moment due to this force P2. So, we have plus P2 times 70, which is the moment arm. This also causes a counterclockwise moment, so it is positive. And we have the moment due to this weight, which is also a counterclockwise moment, so it is positive. So, we have plus W times the moment arm is 35. This has to be 0. So, now we have got the three equations of equilibrium, and from this we can determine three unknowns. But we see that we have 6 unknowns in this problem. So, we have to consider one more free body diagram in order to get 3 additional equations. So, let us consider the free body diagram of the platform, that is CD. So, here you see the free body diagram of the platform CD. The unknowns are the tension occurring in the portion DE and the portion BC, which is T2. From this free body diagram, for the equilibrium we can write 3 equations, 2 force summation and 1 moment equation. Let us first write the force summation, that is sigma Fx has to be 0. So, we have the horizontal component of the force T2 cos theta 2, which is negative, plus T3 cos theta 3, which is in the positive direction, has to be 0. For the forces to be 0, the vertical component has to sum to 0. So, we have the vertical components T2 sin theta 2 plus T3 sin theta 3, the 2 vertical forces at C and D, minus the weight W of the platform to be 0. For equilibrium to exist, the moments have to be also 0. So, either we can take moment about C or D. So, here let us take the moments about C to be 0. So, at C, this force T2 passes through this point C, and so it does not causes any moment, but we have moments due to this concentrated load, the equivalent concentrated load of the platform, and this force T3. So, the moment of this force is clockwise, and so it is negative. So, minus 2000, the moment arm is 15 meters. the moment due to the vertical component of the force T3 is plus T3 sin theta 3 times the moment arm, which is 30. The horizontal force, that is T3 cos theta 3, passes through the point C, and so it does not has any moment. So, this has to be 0. So, if we say that this is equation 4, 5 and 6, we have now the 6 equations to solve for the 6 unknowns. So, if we solve these equations, we can determine the unknowns. Since our interest is only in the shape of the cable, so here after solving we have found these angles as 56.31, theta 2 as 45 degrees and theta 3 as 45 degrees. Now, once we know these angles, we can determine the lengths, that is the length of the portion AB is equal to 10 divided by cos theta 1, 10 meters, which is the horizontal span, divided by cos 56.31, so many meters. It is equal to roughly 18.12 meters. Similarly, the length of the portion BC is the horizontal span divided by cos theta 2, which is 45 degrees, which turns out to be 28.28 meters, and the length of the portion DE is equal to 20 divided by cos 45, which is again 28.28 meters. So, this example completely illustrates the way we solve the cables when subjected to concentrated loads. Let us now move on to discuss cables under uniform loading. This kind of situation occurs in the cables which support the bridges. In the earlier example, we have seen a cable supporting a bridge, and we see that there are at equal distances the cable is tied to the platform of the bridge. So, it is equivalent to an uniformly distributed load in the horizontal direction for the cable. So, let us consider a general cable AC DB, which is tied at this point A and B, subjected to some kind of a uniform loading. It could be varying in magnitude along the cable, either along the cable or along the horizontal direction. So, we are interested to find the shape of the cable under the load, and the internal forces that develop in the cable at any location are tangent to the shape of this curve. Let us say at C, where the tangent of this curve is horizontal, the tension in the cable is directed in the horizontal direction, and at B, where it is fixed, the direction of the tensile force is tangent at this point, and which is also equal to the reaction at this point B. So, in order to solve, let us consider a portion of this cable. let us say this portion CD and draw the corresponding free body diagram. At C, since the tangent to this curve is horizontal, the tension is T naught, which is directed in the horizontal direction. And at D, this tension force T is along the tangent, and we do not know this angle. So, this force T is both unknown in the magnitude and direction. This W is the equivalent load of all these distributed loads. So, let us construct the free body diagram, and from this free body diagram write down the equations relating these forces. One graphical method of solving of the equilibrium, particularly in case of 2D, is using the force polygons or force triangles. So, here you see that method applied. Here you mark this force T naught, T and W, and for equilibrium to exist, the sum of all these forces has to be 0. So, that means they have to form a closed polygon where the ends of the vectors have to meet. So, from this force triangle, we have the horizontal component of this tension T, that is T cos theta, should be balanced by this force T naught. So, we have this T cos theta equal to T naught, and the vertical component of this force T, which is T sin theta, has to be balanced by the vertical force W, that is T sin theta is equal to W. And also, since this is a right angle triangle, we know that T naught is in the horizontal direction and weight acts in the vertical direction, and so this forms a right angle triangle. We have the magnitude of T as square root of sum of the sides T naught square plus W square, and also this angle theta is nothing but tan inverse of opposite side, that is W by T naught. So, these equations come from this force triangle. Now, if we move this point along the cable to any other location, the tension in the cable changes, but we see that the horizontal component of this tension T, which is equal to T cos theta, has to be equal to the tension at this point C throughout the length of the cable. So, the horizontal component of this tension force T remains constant and equal to T naught. The vertical component of this tension equals to the total load carried between the portion C and D, where C is the minimum point on the cable. So, the total load carried in this portion is equal to the vertical component. So, from this we see that the tension in the lowest portion on the cable, that is at C, is the lowest, and as we move along the cable towards the end support, the tension increases and becomes maximum at the end supports, that is at A and B. Let us consider few examples of uniformly distributed loads on cables. One, we call it as a parabolic cable because the shape of the curve taken by the cable is a parabola, and this occurs when the cable is loaded uniformly along the x direction. This kind of a situation can be approximated for cables which support the bridges. So, here in this picture you see the cable ACB supporting a bridge platform which is having a weight W newtons per meter length of the bridge. So, this is connected to the cable through these vertical strings or cables. So, the loading is like a horizontally uniformly loaded cable. If we consider this portion CD and draw the free body diagram, C being the lowest point on the cable, we have the horizontal tension T naught, and at D the tension is tangent to this path, which is both unknown in magnitude and direction, and the total load carried in this portion, which is equal to W times the x span of this cable CD, that is Wx, which acts through the center span between C and D. So, let us find what are these values through the force triangle. The magnitude of this tensile force T has to be equal to square root of T naught square plus capital W square, which is W square x square, and this angle is given by tan theta, which is equal to Wx divided by T naught. Now, let us sum the moments of these forces about this point D. We have this vertical force Wx having a moment arm of x by 2, which causes a counterclockwise moment. So, it is positive. So, we have Wx into x by 2, and the moment of this force T naught, which is a clockwise moment. So, we have a negative moment minus T naught times y, which is the moment arm of this force T naught about this point D. So, this equation relates the y and x component coordinates of the various location of the cable. So, rewriting this equation, we have y is equal to W x square by 2 T naught. So, this is an equation of a parabola. So, we have it in the form y equal to a x square, which is the equation of a parabola, where a is in this case W by 2 T naught square. So, that is why we call it as a parabolic cable, since the shape of the curve taken by the cable is a parabola. And in some problems we may be given the end conditions in terms of the tangent or in terms of the curvature. So, in that case it is convenient to use the differential forms of this equation, that is either dy by dx or d square y by dx square. So, for this cable we have d square y by dx square as W T naught. Sometimes there may be some constants in the equation. Since here we have considered our origin at C, these constants become 0. Else we generally have this equation with some additional constants. So, we will see some example later. Let us consider now the cable which is loaded uniformly along its length, because in all the previous cases we have not concentrated on the effect of the weight of the cable itself. So, the weight of the cable acts along the length of the cable, and in the previous discussions we have not considered the same. So, let us see how the shape of the cable changes if we consider the self weight of the cable. So, here you see a cable ACB where the self weight is considered and it acts along the length of the cable. So, at any point D, which is having a coordinate x comma y, has a coordinate along the length of the cable as S. Let us also assume that the lowest point along the cable, that is C, has a vertical coordinate of, let us say, small c. Let us draw the free body diagram of a portion, that is CD. We have the horizontal component of the force T naught at C, the tension at D, which is both unknown in direction and magnitude, and the weight of this cable, which is WS. S is the coordinate along the length of the cable. So, this is the total vertical weight for this portion CD. The internal tension force T's magnitude can be related to the vertical force W and the horizontal force T naught, or the tension at C, as T equal to root of T naught square plus W square S square from the force triangle. Now, if we write T naught by W as C, then this can be rewritten as W times root of C square plus S square, where C is the ratio of this horizontal tension to the uniform weight W. So, this is obviously from this force triangle. Now, let us relate the horizontal and vertical coordinates with the coordinate along the curve, because the weight is distributed along the length of the curve. So, we should be able to correlate the x and y coordinate with the path coordinate, that is the length of the curve. So, first let us relate this x with the cable length S. So, for that we consider this differential element ds, which spans dx and dy along the horizontal and vertical directions, and write the equation. So, for a very small element, dx is equal to ds times cos theta, and cos theta can be obtained from this force triangle, which is equal to T naught by T. If we find what is this value T naught by T from this equation, we have it as 1 over root of 1 plus S square by C square. This can be quickly found by substituting the value of T and T naught from these two relations and solving. So, we have this dx as ds divided by root of 1 plus s square by c square. So, if we integrate this from this point C to D, we get the relation between the total length S spanned by this segment CD and the horizontal distance spanned by this curve segment CD. So, we integrated between this point and the point of our interest. So, the integral is 0 to s ds by root of 1 plus s square by c square, which is equal to c times of sine hyperbolic inverse s by c, or rewriting this we have s equal to c sine hyperbolic of x by c. So, this equation relates the horizontal coordinate x to the path coordinate or the length of the cable s. So, now let us relate the x and y coordinates of the cable. We may be interested in some cases to relate the y coordinate with the length of the cable also. So, in that case we can again write the equations in the similar way. So, we write again from this differential element dy is equal to dx tan theta, and tan theta we get from this force triangle as w by t naught, which is equal to s by c, and we know that this is equal to sine hyperbolic of x by c from the previous equation that we derived for the relation between x and c. Now, let us integrate this between the limits. So, we have y minus c equal to the integral between the limits 0 to x sine hyperbolic x by c dx, which is equal to c cos hyperbolic x by c minus c. If we rewrite this, it is y equal to c cos hyperbolic x by c, which is nothing but the equation of a catenary. And in some problems we may be interested by knowing the end conditions as the tangent and the end location. So, it is possible to write the differential form of this equation and solve for the same. So, here we have the differential form as t square s by dx square, which is equal to w by t naught times ds by dx. So, let us solve one example problem. So, consider a blimp which is tied to a cable such that certain portion of the cable is lying on the ground and certain portion of the cable is hanging. It is given the weight of the cable as 10 newtons per meter and the length as 400 meters, and as this blimp is flying, it is developing a forward thrust of 100 newtons against the air resistance, and it is developing a lift of say 1000 newtons. So, we are interested to find at what height the blimp is flying and what length of the cable is lying on the ground. In order to solve this problem, let us consider the point where the cable is attached to the blimp as our coordinate reference. So, if we draw the free body diagram of the blimp, we have the 1000 newtons lift generated by the blimp and 100 newtons forward force developed by the blimp and the tension in the cable, say Ty and Tx. This is our origin and this is the positive x and positive y direction. So, from the equilibrium equation we have Tx as 100 newtons and Ty as 1000 newtons from this free body diagram. Now, let us draw the free body diagram for the cable. Where certain portions of the cable is lying on the ground and the remaining cable is hanging, and we have these forces developed by the blimp, and we are considering this as our origin, and this cable is uniformly loaded by its self weight, which is 10 newtons per meter. Now, in order to solve this problem, let us take the differential relations between y and x, which is equal to W s by T x plus C1. This comes from the force triangle. So, if we consider any portion of the cable, we have the horizontal component of the tension force Tx balanced by the tension force T, the weight of the cable which is Ws, and the horizontal component Tx balancing the forward thrust of 100 newtons. So, from this force triangle we have this equation in the differential form. So, we know that at the origin where x equal to 0 and y is equal to 0, we have the length of the cable to be 0 and dy by dx, which is the tangent, is equal to the ratio of Ty and Tx, which is 10. So, if we substitute this, we find C1 as 10. At the contact point where this cable contacts the ground, we have the tangent to be 0. So, we have dy by dx equal to 0 at contact. So, from this we get S equal to minus 100 meters. So, that means the length of the cable between this portion where the coordinate is 0 to the point where it is in contact with the ground is 100 meters. So, of the total length of the cable, which is 400 meters, 100 meters of the cable is hanging, and so the remaining 300 meters is lying on the ground. Now, Let us consider the relations between the length and the x coordinate from the equations that we have derived for the catenary. So, this is the general equation, and the equation that relates the y coordinate with the length. So, here h is the horizontal component is nothing but T x. From this equation, at origin s equal to 0, so we get C2 as minus Tx by W times sine hyperbolic C1. We know this C1 and we also know this horizontal component and the weight carried. So, from this we find C2 as minus 29.98, and at the contact point we know that S is equal to 100, and from this we get x equal to C2, which is equal to minus 29.98 meters. So, if you remember that this is the cable and this is our coordinate 0, and we have found that at the point where the cable is in contact, the x distance is minus 29.98 meters. Now, if we solve this other equation at origin, that is at this point, we have s equal to 0, x equal to 0 and y is equal to 0. So, from this we find this constant C3 as cos hyperbolic minus W by Tx C2. We have already found this constant C2, and from this we find C3 as minus 100.47. At the point of contact with the ground, x equal to minus 29.98 meters, and we substitute this in this equation to find that y is equal to h by W plus C3, which is minus 90.47 meters. So, at the place where the cable is in contact with the ground, the y coordinate is minus 90.47 meters. So, the height at which the blimp is flying is 90.47 meters. So, these examples shows how to compute the shape of the cables loaded uniformly along the cable or uniformly along the x direction. We have to use sometimes the differential forms because sometimes the end conditions are known in terms of the tangents or their locations.